Hey there, welcome to HackerVert. I'm John. Thanks for joining me. We're going to be taking a look at reverse engineering challenge problem in this first reverse engineering sessions. It's funny, I do reverse engineering for a living, vulnerability research, and the more I do it, the less reverse engineering I actually do, which is odd. But I'll talk a little bit more of that as we go on. So here I am at crackmes.1. It's the sort of predecessor to crackmes.de. And what we're doing is kind of looking for anything that's on the Linux platform, looking for x86-64, anything that's been compiled or written in C and C++. And we're going to start reverse engineering. This one I liked. I got into it and just enjoyed the challenge, so kind of kept this one rolling. The password for these things are crackmes.1 or crackmes.de if it's an old enough one that came from that site that got shut down, and the community picked it up and started archiving these challenges and allowing other people to put those challenges in. So that's always a great thing. Well, thanks for whoever's doing that. So we're going to load this into Ghidra. Ghidra is going to be our interactive disassembler and decompiler. It's going to help us analyze this code and get a sense of what's going on here. So what I'm doing is when I ran the application the first time, it told me that shouldn't run applications that you don't know what they're doing, and it created a file on my desktop or at the same folder called "U was hacked" or something like that. So I'm going to go in here and I'm going to take a look at how that happened, what happened, and you'll see as I rename functions, I always do a Z underscore before them. One of my first jobs in reverse engineering out of college, we did that in our malware analysis lab. And we would do Z underscore as a prefix to all the functions that we named. Anything that was named by like an automated system or a signature that we had from previous reverse engineering, we would omit that if we were 100% sure that's what it did. And this gives me kind of the confidence to go through and name functions willy-nilly without being 100% sure. And then at any time I can sort the functions by name, and all the Z underscores at the beginning are things that I know that I affected and I changed. I named those things, or somebody in my group did. So that's why I do that, and I still do it to this day, like 13 years later. All right, so I'm kind of looking through this function, trying to understand what's going on. I know that down here there's just some applications or small algorithms, some addition, subtraction, multiplication, and I don't want to deal too much with trying to name them anything fancy. It's math 1, math 2, and math 3. Going down into the for loops and trying to name these as the indexes they are. If I were developing this, I would start with I, and then any nested variables, I'd be J, K, moving on and on. So the strategy here for me is really just trying to take all of this cognitive complexity with all of these locals and stacks and underscore, like all of this stuff that doesn't make sense to me, and trying to redefine it into something that when I see it, it jumps out and kind of registers, something that I've done, something that I've analyzed and understand. So here, things like argv, argc, and getting an understanding of what's actually going on here is going to help me process this a little bit easier. So there's this application, this branch in the code that says, please run me as /robot1. And my hunch here was that just running it with something that wasn't 8 characters, including the / would cause that to happen. And I was right there. So what we are looking for is just a way to make sure what we're seeing in the code in the decompiled view here is really what's actually happening. So I'll jump back and forth from Ghidra to actually running the application with different things. Here I'm trying to figure out how to avoid this big, wow, it looks like you tried to run me thing. And what we'll see is the local 90 is actually the argv1, or 0 essentially. It's the application name, so /robot. That's actually the 4th index. So down there I did a len on robot 1, which is 8. I indexed 3 into it, which was a O. When you change that to an ordinal, which is just getting the actual decimal value of that, it's 111. Then there's a subtraction of 61. And over on the right side, you'll see the subtraction of 6b. But then over in the disassembly view, it'll say a subtraction of A. So I don't know the functional equivalence of that. We'd have to go back and analyze it a little bit more. But it turns out that what I'm seeing in the decompiled view isn't actually correct in the sense that I'm thinking about it. So going over to the disassembly is often required to get a better understanding of what's actually happening, making sure that you're not misinterpreting something. So here I'm looking at the actual number of values that get inputted. No, this is actually different. I think this ends up being the size of the input that's passed to scanf. So we'll be copying up to 64 bytes, but it looks like it actually expects a specific size, which is 19 bytes. There's some shift lefts and things like that. A shift left by 2 is just a multiplication by 4. So again, going through this, trying to understand what's going on. Some other anecdotes, things from my past. I did say that I did reverse engineering as my first job. My first job was as a civilian malware analyst for the United States Air Force. And I worked with an organization that did, reverse engineering. So I ended up working with a lot of people in the military and really enjoyed my time. And it was a ton of fun, but we reverse engineered malicious software targeting U.S. air and space assets, and it was just an absolute blast. So kind of interesting background, but it was a really good time. Now I do it for different people, but I enjoy it just the same. So at some point in this reverse engineering process, I was looking at all of the things that I need to do, all of the constraints that I need to consider, and down there, sort of the bottom of that disassembly or decompiled view, you'll see this buffer 9, buffer E, buffer 1, buffer 4 having to be specific values. And then if you look down, there's a need to jump around and keep track of every single one of those characters in that 19-byte input. And, I just wasn't really feeling it. I didn't want to continue on that process. So I thought this would be a really good challenge for Angr. If you don't know, Angr is a binary analysis framework. It is essentially a toolkit of lots of different things working together to help you do and solve reverse engineering and other types of interesting tasks with software. One of the most notable features is a symbolic executor, which essentially will take your target binary, lift it into an intermediate language, and then start analyzing it. It'll start pulling out constraints. And then it'll feed those constraints to a backend solver. In this case, the solver that we'll be using is Microsoft Z3. So it'll gather those things, put them all into a form that is suitable for the solver to understand, and then ask the solver if there's any state which satisfies this. And then it'll come back with an answer. So it's really awesome. It's really unique. But the thing is, it actually requires a good understanding of how exactly to ask your questions. It's a very programmatic kind of way to ask for a solution to something. But as you'll see here, what I started to do right away was I just created my solve.py script, started going immediately to the Angr documentation and a lot of the examples that people have written from past CTF challenges. There's one called Wyvern, which is one of my favorite ones to start with. It's really well documented. There's, I think, a good strategy and layout for how you solve these things typically. So I think I started there and then started working my way around looking at different solutions. There's a really interesting way, a sort of exploration technique that allows you to find a specific branch or address and avoid lots of others. So what ends up happening is as you start emulating, as you start symbolically executing this application, as you reach certain points in the application, you'll say avoid these and it'll drop that branch and won't have to view it or keep it in its memory at any point. It can just immediately drop it. So all those locations with avoid are the places where I went and found exit, put all those addresses in there, and the find is where it prints out the correct input kind of happy message. So here I am in Ghidra. I'm looking for the base address of this application. If you don't put one in for Pi executable, position independent executable, it will automatically base it at 400,000 hex, which means the addresses that I put in are not going to resolve. They're not going to be right. So here I am running it. It didn't work. So I'm kind of fine tuning it. The way I like to write these types of things is like almost like working with clay. An artist, sculptor might put a big blob of clay down and it looks like really nothing interesting. And then they'll slowly start moving it into shape and cutting pieces off, adding pieces on. And, eventually they'll come to something that is quite elegant, right? So that's what I'm trying to do here. By really kind of Frankensteining and stitching things together. I don't use Angr on a daily basis, but when I do, I always have a lot of fun with it. So here we are going down this path. So you'll see the references to Clarify. Clarify is sort of like an interface to a backend solver. You'll see things like the solver in this case is Microsoft Z3, which is their theorem prover or SMT solver. When you'll see things like BVS, that means bit vector symbolic. It's a symbolic bit vector. There are different types, and SMT solver stands for Satisfiability Modulo Theory solver. And it's sort of like a front end that reaches out to a lot of SAT solvers. And essentially what ends up happening is there's lots of different strategies based on different types. And one of those most dynamic types is bit vectors. And because we have lots of different types in software, pointers, we have, bytes, we have chars, we have, words and D words and all these other different things that we can put, we tend to start with, I think modeling as a bit vector allows you a little bit more flexibility and freedom to really take on any type of type that you're trying to model and deal with. So that's why I tend to use them. Bit vector value is also using a bit vector that you will pass off to the solver, but that has a very concrete and specific value. It's not symbolic. So bit vector symbolic is, one that the solver will try to solve for. So now I'm trying to understand how to deal with the standard in. I know how to deal with passing in a symbolic app, like hooking memcopy, for example, and then in that buffer, putting a symbolic, just returning a symbolic value, or from the input on the command line, being able to do that. And as I started researching and looking this up, there was something called let's see if I can find it here. Where did it go? Sim file stream on line 20 there, the standard in. What we're essentially going to do is we are going to use this as a way to represent our buffer that we're going to be passing to the application when it asks us. And finally, we got something. You can tell that we got something because there's different states. There's one active, there's one found, and there's a couple that are hit a void, or 17 that hit a void. So now I'm going to try to basically get an answer from the solver now that it got down this far. All right. I can just return this because the value that's returned is print in the entry point of this application, that name equals underscore main. All right, and that's not working. This split new line I don't think should be here, at least for my example. So I'm going to remove that, and I think this is where everything works. There we go. Now you might be wondering why there's so much junk behind this, and we're going to kind of go through that here. There's a part where I try to clean this up and make sense of this. Essentially, the input that this is passed to ends up being 64 bytes, right? Like the actual buffer is like 72 or something. It reads up to 64 bytes. So the actual amount of data that we have, and there I just tested it and ended up working. So we have the solution for this thing. We don't know the algorithm for actually how it works. We'd have to go through and manually do that rather than just getting the solution. And if I had to do this manually, I absolutely could, but I think mocking it out and doing it this way with the solver first to understand what the key is helps you go through the process of manually doing it, at least knowing one solution. But again, I didn't do that. So here I am taking a look at the actual length of that buffer that came back in the result, and that came back as 63 bytes. So what I'm going to try to do is work with this bit vector, this flag, a little bit, and try to understand why it needs that 64 bytes and that 19 bytes didn't really seem to work. So I'm going to create a 64 byte. That's why we had to multiply by 8 because, there we go, that worked. Yeah, so at this point, It's just kind of flipping around the standard in input and trying to understand the best way, or just kind of different ways. Essentially, this solves so fast, like 3 seconds, that I'm not trying to save any time or be super efficient in the way that I'm solving this here. I just want to understand a little bit more about this use of the file sim stream, and kind of playing with the has end of being true and false and watching it work and not work and things like that. But there's ways to model all of these things. You have to read up and look at a lot of examples and just try to get a sense of the best way to actually make sense of all of this stuff. But in the end, I thought this was a really fun challenge. I had a ton of fun doing it, and that's pretty much it. I think when I do these videos again, it'll be a lot like this. And until next time.